Welcome to another video from explainingcomputers.com. This time it's very exciting indeed, as I'm going to do my first ever RISC-V PC build. I'm going to do it using this, the Milk-V Jupiter, which is a Mini-ITX RISC-V board with a Spacemit M1 system on a chip. So let's go and get started. Right, here we have our Milk-V Jupiter, which is available in 3 versions. Firstly, there are boards with 4 or 8 GB of RAM and a Spacemit K1 system on a chip, and these are priced at $59.90 and $79.90. And then there's the version we have here, which is the top of the range model, and this costs $115, and this has got 16 GB of RAM and a Spacemit M1 system on a chip. And I'll explain the difference between the K1 and the M1 systems on a chip when we've opened this up. So let's get on with the unboxing. Very exciting, highly anticipated product for me, a RISC-V system on a Mini-ITX motherboard. Piece of foam on the top, and here it is. Look, let's get it out. How does it come out? Beautifully packed. Come on. Eventually I'll get it out. I can never get these out of the box. There we are. There's the motherboard, and it's in a bag with a sticker. I think we can just open like that. There we go. And come on. Very exciting. And whoa, there's our new RISC-V board. Very exciting board. Anyway, there are other things in the box. We have here, looks like antennas, and down here we've got an I/O shield. But of course, the most important thing is the board itself, in the middle of which we can see its M1 system on a chip. And this has got 8 Spacemit X60 CPU cores, along with an IMG BXE232 GPU and 2 TOPS of neural compute power. And this is the same specification as the Spacemit K1 as I've tested on other boards, such as, for example, this Banana Pi BPI F3. But if we looked under the heatsink on this board, its K1 chip looks like this, whereas the M1 on our top-of-the-range Milk-V Jupiter looks like this. And so, as we can see, the difference between the K1 and the M1 is that the M1 comes in a package with a metal heat spreader. And, in turn, this allows the M1's X60 cores to be clocked at up to 1.8 GHz rather than 1.6 GHz for a K1. And so, our Milk-V Jupiter offers 12.5% more CPU performance than K1-based RISC-V systems. This said, no heatsink is provided with the board, although we can clearly see the outline for a heatsink and a mounting hole, so I'll have to sort something out. Next to the SoC we have our RAM, which, as noted earlier here, is 16 GB, and it's a low-power DDR4, and then just above the SoC we have a socket for an eMMC flash module. Turning to the back panel, we first find a barrel jack, which can be used to power the board with a 12-volt 3-amp supply, and then next to it there's a USB Type-C connector, and this is USB 2 OTG, and it can be used to write an operating system to an SSD or an eMMC flash module, and it can also be used to power the board. There's then a full-size HDMI connector, and this supports up to 1920 by 1440 at 60 frames a second. And then along from that we have 2 1 gigabit Ethernet ports, 2 USB 3 ports, 2 USB 2 ports, and 3.5mm audio out and microphone sockets. Nipping around the corner, we then find a header for 2 more USB 2 ports and another for 2 more USB 3 ports. And if we pull out a bit further, we also find some PCIe connectivity. This comes in the form of a x8 connector, and this offers a PCIe 2.12 lane interface, and I look forward to testing out this slot later in the video. And we also have an M.2 slot, and this is M-keyed and supports all common lengths of NVMe SSD, and this has got a PCIe 2.0 two-lane interface. And you won't be surprised to learn that we'll be fitting our system drive in this slot. Rotating 90 again to the back edge, we find a front audio panel header and a microSD card slot. And it's worth noting that the Milk-V Jupiter can boot from microSD, an NVMe SSD or an eMMC module, with the boot priority being in that order. Also on the back edge we have a standard 24-pin ATX power connector. I think this is great to have one of these on a RISC-V board. It makes it feel just like a real PC. And in this build we will be powering this board using a standard ATX power supply. Just behind here we also have headers for powering two SATA SSDs, although if SATA SSDs are connected, and we'll be trying one later via a PCIe adapter, they can of course be powered via a standard ATX power supply. Taking a final spin, on the last edge we have a front panel header, a UART header, an eMMC flash module header which disables the SBI boot flash if required, another UART header, a recovery header and a wireless module that supports Wi-Fi 6 and Bluetooth 5.2 and which has got two of those very tiny IPEX1 antenna connectors. Other than this, also on the top of the board are a fan header, a real-time clock battery socket into which will be fitting a CR1220 cell, and a recovery button. And the reason this is here is because if we want to write a system image to an NVMe SSD or an eMMC flash module, we can do so by connecting the board to another computer via its USB-C OTG port and pressing either this recovery button or shorting the recovery header I just mentioned. Finally, if we take a look underneath, we can see there are no significant components, although over here there are header pads labelled LCD, CAM1 and CAM2, which is interesting as these are not listed anywhere I can find in the board specification. And so there we are, the Milk-V Jupiter, which even with 16GB of RAM is a reasonably priced Mini-ITX RISC-V board, and which I think is now crying out for a case. Well, here's the case we're going to be using, good and solid. It's an in-win shop-in Mini-ITX with a 150 watt power supply which has got a very quiet fan. And I first used this case in my ARM PC build, in which it was fitted with a ROC-V ITX. But I've now removed that board and its I/O shield, so everything is ready for the Milk-V Jupiter. Talking of which, I've now fitted our RISC-V board with a CR2012 real-time clock battery as well as a 500GB Crucial P3 M.2 NVMe SSD. This is a PCIe Gen 3 drive which is fine in the slot with a two-lane PCIe 2.0 interface. I've also added a heatsink. This is a 40x30x10 unit made of two smaller units glued together, and it's fixed in place with a thick heat pad on one side and thin thermal tape on the other, as the RAM chip is not as high as the SoC. This is the same cooling solution I used on the Banana Pi BPI F3 we saw earlier, and I did consider using a much larger heatsink, specifically this one. This would have been better in terms of actually taking away more heat, but I was worried about having this in place only held in by thermal tape. I'd like to have this somehow secured to the push pin holes there, but I haven't got a heatsink which will fit with that, so for now we will stick with this arrangement. So let's continue our build by fitting the I/O shield, which goes in here. Will it go in easily? Please go in easily. Oh, that's not bad. I hate fitting these, as some of you know. There we are, that seems to be okay. And we can now bring in the board, which is going to be very tricky to get in. Not quite sure how we're going to do this, but I will prevail. Oh, that wasn't too bad, was it? That went in easier than I thought. So let's just get it in place. It's caught somewhere down here. What's going on? There we are. That is just right. So let's drop in some screws. There we go. I do like putting a computer together. It's just fun, isn't it? Although the next bit is getting all this wiring in, which is not going to be quite so much fun. We need to get in for a start. This is the front panel connector. I'm certain, so let's get this down here before we try fitting the power supply. I know you can't see these very well, so I'll just put these in as easily as I can. Try and put that wire out the way. And now we'll fit the ATX power connector. There we go. And we've also got to fit front audio. There we are. And finally, we're going to be fitting our front USB connectors, which go in down here. Nice little click as they went in. So, and I just have to find some way of getting this wiring as neat as I can. There we are. And I fully accept this is not very, very neat, but that's as good as we're going to get at the moment. And indeed, for now, I'm not going to put the top on the case because we need to get to the recovery button down there to assist in installing an operating system on the SSD. Greetings! I've now got the system all connected up and running. There's a little blue light on under here, and if we go across to the HDMI output, we are booting into Bianbu, which is a version of Ubuntu from Spacemit customized for their RISC-V hardware. And I installed Bianbu on our NVMe SSD by connecting the Milk-V Jupiter to another computer via its USB-C OTG port and pressing the recovery button when powering up. And I then ran a Spacemit program called Titan Flasher, which very straightforwardly wrote the operating system image to our SSD. Anyway, here we are arriving in Bianbu OS, so let's log in. And as we've seen in some other videos where I've been running Bianbu OS, it's quite a nice operating system. It's very stable, although it can be a bit sluggish. And initially here, let's just go to a terminal. Here we are, and let's just check what we're actually running. We'll do an ls CPU, and there we are. We can see we've got our 8 Spacemit X60 cores running it up to 1.8 gigahertz. And let's also clear the screen and do an ls BLK so we can see the block devices on the system. Basically, we've got our NVMe SSD, and as we hear, let's test its speed. Here we go. What are we going to get? Remember, it's only on a PCIe 2.0 interface 2-lane, 472 megabytes a second. Not dramatically fast, but far better than running from, for example, a micro SD card. If we just close this down, we'll have a look at the other software that is pre-installed. We have here, for example, LibreOffice Writer. I always like to run up LibreOffice Writer. It shows that we are heading towards, with RISC-V, a credible end-user computing system, doesn't it? We can run things like LibreOffice. We can do standard computing tasks. As you can see, it takes a little bit of time. It'll get there in the end. Let's encourage it. Come on, you can get there. And go on, just for us. There we are. We've arrived in LibreOffice. I don't want the tips. Go away. I just want to type hello like that and make it very, very large, because I always do, because it is the law. There we are. LibreOffice is clearly working. And also pre-installed, we've got, for example, Shotwell to deal with photographs. We've got the other parts of LibreOffice. We've got Rhythmbox. We have got the system monitor. Let's just bring that up, give you a feel of the system. There we are. Reasonable temperatures. We can see all of our 8 cores there. And things are generally okay. We'll just take a look at applications. I have installed some applications here, so we've got some extras in this. In addition to what comes with it, I have, for example, installed GIMP, the GNU Image Manipulation Program. Good to see this works. Not everything works. I tried to install Sysbench, for example, and Sysbench, no candidate available, couldn't install Sysbench. But I have, as you can see, installed GIMP, and it does work. We can do a new document like that, and OK. And let's do a filter. Let's just render something simple. Let's render, for example, I don't know, a maze. And oh look, we've rendered a maze. You can see GIMP is working here on a RISC-V system. And do we want to save this? No, discard our changes. I've also installed, also under graphics here, Inkscape. Almost couldn't find it there, but there it is. Takes again a little while to come up, but it does work. Let's just speed on through. Although, as we can see, we've got a working version of Inkscape. Think where we were with RISC-V, what, a year or two ago, 2 or 3 years ago? This stuff was so far away. We've now clearly coming towards a world where RISC-V will offer a viable choice for desktop computing. And I've even installed Critter, and Critter is very, very slow. But again, I just want to show you it does actually work on this RISC-V system. And here we are running Critter. Although, as I said earlier, it is painfully slow, absolutely not yet usable, but imagine a RISC-V system with 5 or 10 times the power, and that's perfectly possible in the next few years. And again, we're getting there. I am impressed with the speed of progress, software and hardware for RISC-V. And of course, I've got to show you performance of a browser. So let's run up Chromium, see what that can do. It'll probably do browser type things, won't it? Because that's what browsers do. Here we are, we've arrived on the Explaining Computers website, where we could learn about, for example, RISC-V. Oh, it all links together, doesn't it? But I'm sure you want to see streaming media playback, so let's just take a look at that. And here we are. It took a little while to settle down and get things playing properly full screen, but now we've achieved that, playback is pretty good. And so once again, as on other K1 or M1 based systems I've tested in 2024, we have got decent streaming media playback on a desktop RISC-V system. Now, at this point in proceedings, I had planned to test out some PCIe cards in our PCIe slot, specifically this PCIe to SATA adapter, and also down here this PCIe to NVMe SSD card. But unfortunately, I've been an idiot, because I was under the impression all the way through planning this video that this case was designed to take a low profile PCIe card, but it clearly isn't. I have no idea why I thought that. There's nothing to take out here so you can fit a card, which would go in that way around. And I think that it's because the case has got the height for it, but the motherboard here is fitted quite high in the case because the compartment underneath it takes drives. But anyway, I can't fit this card or any card into the slot in this case. And so what I need to do is this, and here we are running the board out of the case, still powered by the power supply from the case, still hooked up to its front panel connector, but I'm now able to fit the card. I have fitted the card, as you can see, the SATA adapter card, and I've also connected to a SATA SSD. So let's go across to the desktop, where in the terminal we'll do an ls PCI to see the PCIe devices on the system. And yes, we can see at the top we've got our NVMe SSD, and below that we've got our SATA controller we just added. And we clear the screen to be neat and tidy and do an ls BLK, list block devices. We've now got the SATA SSD in addition to the drives we had earlier. So once again, I'll keep things neat and tidy, and we'll do a speed test on the SATA SSD. Here we go. Let's see what speed we get. It's clearly working. It came up in there, the listing of drives. Not expecting any problems. There we are, 271 megabytes a second. That's not bad, although if you can hear some hesitation in my voice, it's because when we tested the Lichee Pi 3A recently on the channel based on a K1 RISC-V system on a chip, that gave us better speed test results for both an NVMe SSD and a SATA drive connected via a PCIe to SATA adapter. Specifically, the SATA speed there was 316 megabytes a second, and we got 608 megabytes a second for an NVMe SSD, and we were using identical drives. Anyway, the final thing I want to do is this, where, as you can see, I've fitted the PCIe to NVMe adapter card with another crucial P3 NVMe SSD. So let's return to the terminal and execute an ls PCI. And there we are. We've now got two identical Crucial P3 SSDs connected to the system. So if we do an LSBLK, we should see that. Yes, we've got the two NVMe SSDs. And if we test the speed of the second one, what are we going to get? There we are, 489 megabytes a second. So again, speed is slightly disappointing, but the Milk 5 Jupiter does offer a good range of storage connectivity. Right, I've put the system back in the case where it belongs, at least for now, and over on the desktop here in Bianbu, I wanted to show you before we finished that I've managed to install Kdenlive on this system. Now, I have run Kdenlive on a RISC-V computer before. I've run it on a Lichee Pi 4a, but I haven't got it working before on a Spacemit based system. And to be honest, this isn't really working. It is painfully slow. It's completely unusable, but it does come up. It is rendering video appropriately, just at a very, very, very low speed, as we can see. But for me, this is exciting, as again, it shows us we're heading towards RISC-V being viable on the desktop. I'm sure some people in the comments are going, but Chris, you can just get a computer that works now based on x86 and ARM. Why are you concerned about RISC-V? It's because it's a frontier. It's because it's something new. It's been delivered before our eyes. Over the next few years, RISC-V, I am certain, is going to become a viable end-user desktop computing platform. So there we are. I've completed my first ever RISC-V PC build. And I've done it in my test Mini-ITX case, and in fact I've got another project coming up using this case fairly soon on the channel. I've got to figure out how to make it work, but that should be a very exciting project indeed. But now that's it for another video. If you've enjoyed what you've seen here, please press that like button. If you haven't subscribed, please subscribe, and I hope to talk to you again very soon.